We really appreciate your time. We really like doing these events. We think this is a great place to share ideas and to share some of the knowledge that we've collected and that you can share amongst yourselves as well. So if there's at any point some contention or you have some idea or you've seen something done as I talk through this, please feel free to say so. We will talk about a number of things today, trying to cover fairly broad range of what we call industrial best practices for using natural gas the most efficiently. Not all of them will apply to all of you, but all of the principles will apply to all of you. So if you just take one or two principles out of this workshop, we have done our job well. So let's start. I don't know how many of you actually, we don't speak much about that, but this whole thing, this whole demand-side management that we do falls under a program that we call demand-side management at Enbridge, and it's called slightly differently in Union Gas, but we covered, between the two of us, we covered the whole province, and essentially what we do, we're trying to help our industrial customers use natural gas most efficiently. We give you incentives for that, but most importantly, we give you our attention and our knowledge, and we can give you an ideas that otherwise would be missed. So the reason I'm saying I'm putting emphasis on program is because nowadays we have auditors who come and ask about our program to a select group of customers afterwards. Customers don't even know this under a name of the program. We just come and we help you out. We've done this for over 20, now close to 25 years. So we don't actually call it a program, but it is a program. So that's why I'm putting that up there. And what do we do is essentially we start with the knowledge development. We're giving you, hopefully giving you information you didn't have before or remind you of some information that you had but you since forgotten. So arming our customers with knowledge is step one in actually getting energy efficiency being implemented in places. The next step, of course, is now that you have knowledge, what you do with it. It's identifying the opportunities. Where you're going to find the opportunity to save energy or use it the most efficiently. Again, stressing most efficiently rather than saving, because often some of the projects that we will do will not be seen on the meter. You will not see drop in your natural gas usage, but you will see increased production, increased quality, increased safety, whatever it is, by using the same amount of natural gas. That's also as good as option as actually saving on your meter. The third step is, of course, sometimes we need to quantify the opportunity. It's all nice and dandy to say, yeah, there's opportunity there, you should be turning down your make-up air units, but how much will I save through doing that? So we help with that as well. We're giving you ways to meter the usage if need be. Fourth one is, of course, our engineering hats are on. All of us are engineers. Most of us are professional engineers in province of Ontario. And what we can do is analyze and interpret the data. You have the opportunity, you metered it, you have the data, how to interpret it, how to relate it back to actual savings is an important step. So for those of you who need help or assistance with that, we're there to help you with that. And the last step, of course, is action and implementation. After all this is done, hopefully there is an action and implemented project, because those are the things that will actually save you money in the end. All the other things are just preparatory steps that help you get there. And then things starts again, continuous improvement. You find another knowledge place, you find another opportunity, and it all goes again. So how do we do this in dollars and cents? So knowledge development, that's free. Those are the workshops that you come here. Those are the newsletters. We have a portal on the website that you can come, use some simple calculators. All those things, case studies, hopefully that helps you building up the knowledge. The opportunity identification, as I said, we can come and work with you on finding the opportunities for you. If you feel that third party can do that better for you, we have up to 50% of the costs coverage on some of the financial incentives for you as well, as long as we get the scope of work before and we know what's going on. Same with the metering. If for whatever reason our meters that we have for water, for some natural gas, if those are not enough, we can cover up to 50% of the costs of the meters that you would install on your own, and then they're your meters. You don't have to worry about returning them. Engineering analysis, same thing. Sometimes your process will be so complicated that it will require a very special engineering detailed analysis. We would cover 50% of the cost for that as well if it leads to the energy reduction project. And once all this is done, once you actually go in and implement the project, we offer financial incentives based on the savings, annual savings of that project. It's based on cubic meters saved. For the first 50,000 cubic meters, you get 20 cents. After that, 5 cents thereafter for every cubic meter, up to 50% of the costs. One thing that to keep in mind in all of this is that we offer only customized solutions. So we will hook you up with prescriptive solutions if that's the right solution for you. But for most of you, you have such a complicated environments that really prescriptive solution where you buy something efficient, we give you a coupon is not really applicable to you. So we offer these customized solutions to you, and it's customized to your facility. We work with each one of your facilities to actually understand what you do, how you do it, and then we fit the solution into your facility, rather than just saying, this is a template, you should be fitting into this. If you're not in this template, too bad for you. That's not what we do. And of course, you have this personal interaction between energy solution consultants, people in blue, and your contacts at the facility. To me, that's the advantage of our program. Those energy solutions consultants are the ones that are at the center of everything. All of this would not happen without energy solutions consultant who knows what they're talking about, who are confident, and who are willing to put a lot of work into it. A lot of times you will only see a tiny bit. It's like an iceberg. You will just see the tip of the iceberg of the work that we've done. So when we bring a spreadsheet to you and we say, these are the savings that we think you're going to accomplish, there's a lot of preparatory work that that person has to do in the background. And I'm not saying that to feel sorry for ourselves. That's not the point. The point is that just because it seems like a simple spreadsheet, it's not something that we have at the back of our pockets and we just fill out a couple of things and we bring you back. It takes real work and it takes knowledge. And then if we ask you questions, we don't ask you questions because we want to just take up your time. We ask questions to better understand your situation. The other thing that is really important in my mind from energy solutions perspective that we offer is, I don't know about your facilities, but in my facilities where I used to work, we used to do things always the same way. We know how we do it. We always had the same people, and we always got the same results in the end because we never tried anything different. So when I was hired in my previous role in a tier 2 manufacturer for automotive, I was actually hired from out of automotive sector. And my boss told me that that's exactly what they wanted because they didn't want somebody who comes from the same perspective. So we had people from all walks of life that were hired, and we were pretty good at it. We came up with pretty original solutions. We had, for Toyota, we had 2 patents that nobody else had, and therefore we could be the only supplier in North America for them. So that took some work. Same here. Energy solution consultants come into your facility trying to understand what you do, but also gives you a different perspective so that you don't always repeat what you do day in, day out. That can be good or bad, and we are not going to go and say that we know everything, but offering you different perspectives sometimes gives you something to think about. So now that we know how we help you, why would you even want to be helped? Why would you even want to have energy efficiency in your facility? That's the question that we always ask ourselves, because if it's not good for you, there's no point in us offering the services. That's simple as that. And I like this slide. I've done it before, but I like the slide because it gives us a different perspective. We all have different reasons why we win jobs. We have the car that nobody else has. We have the process that nobody else has. We have some unique thing that nobody in the market has, and we bring that to the market as a benefit. That's a benefit that our company provides to the marketplace. On the other hand, no benefit is any good if it costs an arm and a leg. Nobody's going to buy it. So we need to keep control of the operational costs. And that control represents our cost advantage. So now we have a benefit, we have a cost advantage. That intersection in between the two, that's our value proposition. That's what each one of your companies bring to the marketplace, that value proposition, why people buy your equipment, your things, rather than somebody else's. So if you think about that, you have to control the costs, and reducing energy consumption does reduce your costs. It may be a lot for some of you, it may be a little bit for the others, but it always reduces the cost. So you're increasing your cost advantage by doing that. But unlike some other cost-cutting methodologies, reducing energy consumption helps with all these other things on the other side. It enhances working conditions. If you, for example, if you balance your makeup air, if you provide proper makeup air conditions. It improves public image because now you're using less fuel. It reduces your carbon footprint, so you can put that you're green on your website. All of those things add to the benefit. So you're not only increasing your cost advantage, you're also increasing the benefit you bring to the marketplace. You're increasing your value proposition. There is no other cost-cutting measure that does that other than energy consumption. If you push your supplier for the cheaper cost of the materials, you will eventually get to the point that your materials will not pass QC. Or it will pass QC, but it will be very difficult slog to get there. If you push your labor force to be cheaper, you will eventually find that they are disengaged. Therefore, your productivity will drop off. Energy consumption is the only one that you can freely reduce as much as you want, and you'll still get benefit on the other side. The other thing is this statistics. 20 to 50% of all the energy that industry is using is waste. And every one of you probably thinks, nah, that's somebody else, that's not me. I guarantee you that you're probably on the higher end of that 50%. Every one of you. You just can't help it. That's just the nature of the business because all of us work with fairly old equipment. Very few of us work with the equipment that's cutting edge and new. And it was designed for different times, for different throughputs. We make it work. You guys make it work every single day. And it's a great accomplishment, but it's not energy efficient accomplishment. So what happens is, as a result, you have a lot of waste. And biggest obstacle to that recovery, they found to be a lack of viable end use, where you're going to put waste heat, or payback periods. Payback period is just too long to actually work it. So you're stuck. Nothing happens. So hopefully we can come in and give you some ideas where to use it within the payback periods that you have. We very rarely even put on the table ideas that will give you payback periods of 5 years. We know that doesn't fly in the industry today. Year, 2 years maybe, tops. That's what we're looking for. So when we say, well, we can't find any solution, doesn't mean there's no technical solution. It means there's no technical solution within 5-year payback period, for example. The other thing is, Environmental Commissioner of Ontario in 2016 said that customers save $2.67 for each dollar spent of energy conservation. In other words, energy conservation pays back in multiples. If you look at that payback scenario here, there is no other investment that you can do today that is going to pay you back 267%. So now we know how to do it. We know who can help you. Let's try to find some energy efficiency opportunities. Let's just hash them out. When I talk about energy efficiency opportunities, I talk about 3 R's. Number one opportunity that we always look for first is to reduce or avoid the heat loss altogether. It's the cheapest thing to do. It's least intrusive thing to do. And that's why it's at the base of the pyramid. That's the one that you should be looking the most often for. Recover the waste heat that you cannot avoid. So if you build up all the losses out of the system, what you have left is still some waste. Can you use and recover it somewhere else in the process? Only then, once those two are used up, we go to replacing the equipment. Replacing equipment is a very nice thing to do. It's shiny. It's fresh. Sometimes, most of the times, I would argue it's easier than actually fiddling with something that's existing and trying to make it work. But often you run in the problem of payback periods or just not having capital costs. It would be really nice to build a new facility, spend $100 million, start from scratch. How many of you have that? Right? So let's deal with all of those step at a time. A reminder, when we talk about thermal energy, unlike electricity, thermal energy is only used in two main streams. One is seasonal. In other words, your usage will be driven by the seasonality of the weather outside. And the other one is a process. You just have to use it because you're processing. You have ovens, you have something to heat all year long. Forklift trucks, that's a process, for example, because it's nice and steady throughout the year. So where do we look for? Process equipment, obviously, falls under the process load. Energy converters fall under the process load, your boilers, your, on the electricity side, your compressors. On the other side, you have makeup air units and space heaters. Those are the ones that fall under the seasonal load. So on the first blush, when you look at makeup air units, space heaters, all of us understand it. So seasonal load, everybody immediately says, oh, that's a space heating load. That's for heating the space. But when you really look at it, and you split that and look at it this way, how many of you will actually find that your makeup air is influenced by your process load, really? So therefore, your makeup air plays far more important role for most of you than just space heating, or hopefully it does. And therefore, can anybody think of two examples of the seasonal load that's dependent on the process? Bill? Paint. One is silos, for example. If you have tanks outside and you have to keep them warm for whatever reason of your process, you're processing some sort of chemicals that needs to be kept warm, that will be process load that's driven by seasonality. But far bigger is what Bill said, paint. Paint process, finishing ovens, those kind of things will be driving your seasonal load by a factor of probably 20, 30, 50 to 1 relative to your space heating load. So when you think about where to save energy in industrial facility, not in a facility like this, but in an industrial facility, you really shouldn't be looking at space heaters unless you exhausted all the opportunities for savings, because that's a minute part of your usage, and you should be focusing on makeup air and your process. And we'll talk about both of those now. So let's start with the makeup air. Natural gas consumption, if you draw it out month by month, should be looking something like this. Some of you will have more flat profile, some of you will have more U profile, depending on your loads, but it will look something like this. So if we eliminate the bottom part, if we say June, July, August, there is absolutely no way you're actually using any heat for heating for seasonality purposes, then what you are left with is your process load. This is your process load. So if this is representative of your facility, this big U shape, and you're left with this process load, don't be looking at the process as your number one opportunity to save energy, because you'll be using a lot of effort and money without much payback. What's left, once you take out the process load, is something like this for that particular example. So that's your seasonal consumption. So if that's your particular facility's profile, that's where you should be looking for opportunities. And when you look at seasonal consumption, as I said, do not think space heating. For manufacturing facilities, seasonal consumption, space heating are completely two different things. They shouldn't be used in the same sentence. There's a component of seasonal load that's related to space heating, but it's very small, and it should be talked about separately. So how do you know which part is which? The best way to do it is to do air balance. Every now and then we will have air balance campaigns where we help support air balance by providing 100% of the cost. Many of you have taken advantage of that in the past, and many of you have been surprised by the results you've gotten out of it. But what you get out of it is a very good idea. What is the role of ventilation for your facility? Rather than talking in generalities, what is the role for your facility? To start with, as a basic principle, if you're in this room, for example, like this one here, and if this was your manufacturing space, all the makeup air, all the fresh air that you would have to supply is about 20 cubic feet per minute per attending. So for each one of us, 20 cubic feet per minute, that's all you have to supply. So 20 people times 20, 400 CFMs. 400 CFM is all you would have to supply here. Have you ever seen 400 CFM makeup air unit anywhere in your facility? Probably not. You probably have to add 2 or 3 zeros at the back, right? So that makes you wonder why. If it's good for this, why is it not good for the facility? And the reason is because there's processes going on. There's ovens that take up some of the air from the space, and they exhaust it out. There's some other, let's say, E-coat paint lines. There's other paint processes that require some air to be moved through it. As the air is moved through it, you have to make it up. So now, makeup air therefore is driven by the exhaust, and it should be usually interlocked with the processes. Very few people will have that. Very few people in your facilities will actually interlock makeup air with the process because everybody's afraid of poisoning their fellow human beings. But that's not what's going to happen. If there is no exhaust from the facility, there is no need to make up any air. Direct fired makeup air units, very common in industrial facility, the most efficient way to provide makeup air if you have to provide some. So it's very popular. For them, you have to also provide some exhaust because they put products of combustion in the place. So if you have 100,000 CFM makeup air units that are direct fired, you have to have, by TSSA rules, you have to have 100,000 CFM thereabouts interlocked to that makeup air. Again, most of you will not have it interlocked because you're grandfathered from God knows when and just keeps going on. So it will not actually be interlocked. It should be, but it's not. And you can convince that, I know that many of you are questioning that, but you can go and turn off your makeup air and see how many exhausts turn off at the same time. And it probably won't be many. You would be surprised. So let's take a look. This is a reminder for me. This reason of interlocking, if you really do it properly, is why makeup air should not be used for space heating. As I said, here you get away with 400 CFM of fresh air, so which means that you have to evacuate about 400 CFM of air. And then you can use the baseboard heating or some other ways of heating to actually keep us warm. So keeping us warm, keep the space warm, plus 400 CFM of air is not bad. But imagine how much heat you would need in here if you now put 40,000 CFM of air blasting through this place. Either that or it would be really cold air. So the more makeup air you put into the facility, the more heat you have to provide. So heating your facility with makeup air is a bad idea. Bad. Expensive. So we said that exhaust volume drives the processes. Process, whatever you have, usually on their drawings when they supplied you originally all these fancy processes, they put how much exhaust they require, each one of them. So that's your exhaust volume out of the facility. That's what you should be exhausting. Add 10% if you want to be safe or some such thing. But that's your exhaust volume needs. So whatever your exhaust volume you have, now you have to bring that air in. So you need more. That defines your makeup air volume. If you have too little makeup air volume for the same amount of exhaust, the rest will be made up by the cold air that will infiltrate from all over the place. When you walk through your facility, you walk inside the facility and the door slams behind you, that's that infiltration working. Right? So it's in best interest to actually have that balanced. Again, most of you will not have it balanced, but that's the idea. Exhaust volume is your energy driver, not your makeup air, exhaust volumes. So if you look at exhaust volume, function of process requirements and indoor air quality requirements, and each one of you will have different requirements for that, but once you know what it is, that's what your makeup air volume should be. That's what defines it, no more, no less, somewhere around 100%. And what often happens if you have unbalanced building, if you have a lot of those infiltration that closes the door behind you, you call somebody and they say, yeah, you need more makeup air. Yeah, okay, that's all good. But how much does it cost you to put another makeup air unit? How much does it cost you to run makeup air unit? Well, we'll discover that a little later on. Each 1,000 CFM of makeup air costs you about $1,700. How many of you have installed anything that's only 1,000 CFM recently in your facility? Even those tiny little, roof fans are 5,000 CFM, 10,000 CFM, 20,000 CFM. So multiply that by 10, that's $16,000. Every 10,000 CFM, $16,000 in money. So when somebody says, oh, you're a little negative, I'll put another 50,000 CFM makeup air unit on your roof. 50 times $1,680 every year that you will be paying for that privilege. So if you're not sure if that's the right solution, call us and let's discuss it. Because most of the time your exhaust volume will be wrong. This, putting the makeup air would be the right solution if your exhausts are correct. Most of the time. I've seen now, I'm going to guess at 90% of the cases that I've seen, exhaust volumes were not correct. So let's take a look. I'm a visual person. I like these. So this helps visualize it. If we have a process that requires makeup air, we have to put exhaust. We have to exhaust it. We said that now we have to replace that, so we put exactly the same amount of makeup air into the facility. All fine and dandy. Works great. You installed it in March. Everybody's happy. But that also, there's some shell losses, so it gets warm around it. So comes July, August, people around the facility start to complain, especially the guy who has to sit right next to it because he's monitoring, the little panel there and is making sure that widgets go in and out correctly. Now he gets a little warm. You give him a water bottle, that's not good enough. He wants to walk off the facility. He says, it's 38 degrees Celsius in here, I'm off. What does your plant manager do? Oh, damn it, just put more exhaust. Get rid of the heat. The more, the better. And it is the right solution for the summer. Absolutely, you have to get rid of that. I worked in a facility where we made coils for the cars, springs. We made 16 million of them a year. And you do it by heating the steel rod to red hot, and you wind it, and then you anneal it. We had 12 furnaces inside, high heat ovens, annealing ovens. It was hot. So if somebody didn't want to put exhaust in the summertime, they would be crazy. There is no way you can work without it. The problem is that those exhausts are put one at a time, and we never have time, and we never have money to actually interlock them to anything. They're just there. Because in August, you don't need to interlock them. The more they run, the better. So the problem, of course, comes when the March again rolls around, or January. All those exhausts, see how you have only one out of those 4 arrows balanced by the makeup air? Well, the rest comes from here. We all like to blame shipping doors, but really it would come from anywhere. It just wouldn't stop. You can close that shipping door, it would come from somewhere else. And it would be cold air because you're not preheating it. So the guy at the shipping area is freezing. So what do? We start investigating how to heat the guy at the shipping area. So we look infrared. You put it over shipping doors. It's nice, neat solution. Not too much cost, not too much hassle. Gives us radiant heat, but what the heck does it do for 10,000 CFM of air that's just blasting along? Absolutely nothing. So the guy standing right under it is warm, but the guy behind him is cold still. And you spend the money to install this. So then we go, okay, we have shipping doors. We'll put dock seals. Yeah, okay, we'll put dock seals on 2 of the doors. Third door will be open, and now all of that volume of infiltration air will come through the third door. You solved, again, nothing. Spend the money, you solved nothing. Air curtains, another popular solution. You have ambient filtration. And if you beat it up with the faster air coming from up there, you'll eventually beat that infiltration down and you'll have less infiltration. The problem is the faster this infiltrating air comes through, the less effective air curtain is. It starts at about 70% effectiveness to begin with. By the time you have any sort of negative balance in the building, you will be at about 25, 30% efficient if you're good. So again, you didn't solve the problem. You spend the money, you didn't solve the problem, and you added electrical load to boot. So all of those solutions are not bad, but they're not the right solution to balance your building. So what is it that we really need? Because what will happen is you put the infrared heater there, and now at best, if you didn't do anything else, now you have cold air. You have cold and drafty environment. How many people work in a place where in the middle of the winter you walk by some place and it's nice and toasty and warm. You walk 20 feet away and you feel this cold, drafty air going out. That's normal. That's the result of that. You can't help it. It's physics. So real solution is really to balance the building. You have to balance your building. You have to find a solution to say, I need this much makeup air and this much exhaust. So this whole thing is nice to talk about, but people, intuitively we know what happens, but nobody really visualizes it in one spot. So we thought instead of doing our usual activity books that you have here, so instead of doing this, we will actually do some hands-on things. So our Louise here will guide you through one of the examples. We have a nice little mini factory there on the table, and if you could all just walk up here and see what happens when we have different amounts of exhaust, makeup air. So please feel free. Okay. So now that we've seen the example of what additional exhaust can do, the question is always this. And this keeps coming up in one form or another. But I need all that exhaust. I can't help it. That always is a question. It always comes up. It's always an excuse for doing nothing or just adding makeup air because it's that simple solution. So what we see is very common to exhaust 150,000 CFM or more. That's a very common thing in Southern Ontario. It happens all the time. I'm never surprised when I see 150,000. Now I'm beginning to be surprised when I see I've seen the last report air balance that we've done. It has 385,000 CFM of additional exhaust in a facility that's about 150,000 square feet. So 150,000 CFM, that's pretty much average in Southern Ontario that you see. And they all have their reasons why they have to exhaust. My God, people would die, people would freeze, people would do all sorts of stuff. We just have to do it. But nobody is willing to actually pony up and do the assessment of it. For some reason, people are very leery of doing assessment. These days, indoor air quality assessment can be done for less than $5,000. We can support that with 50% of the cost for you to find out, do you really need that exhaust? The problem is even when they get this study, most people are not willing to fight the results. And results are always, you don't need that air. Almost never. So if somebody is really serious about reducing the exhaust, they need our help by supporting the indoor air quality study. We will help you out with that. But then we have to take it up to the next step and actually fight for the implementation of it. And these are the potential savings, $252,000. Because when you turn off the 3 times exhaust volume, those exhausts, the fans themselves, are not taking just thermal energy out. They're also taking a lot of electricity out. I saved one facility in 2012 when I worked with them. By reducing their exhaust, they had 400,000 CFM of additional air that they didn't need. We turned it off. We saved them 1 megawatt of electrical power a year. So you're talking, everybody's, natural gas doesn't cost anything. It's all fine and dandy. But once you start talking and adding the electricity to the mix, all of a sudden it becomes important. You look at those fans that you have up on the roof. They're 5 horsepower, 10 horsepower, 20 horsepower. Those are not free horsepowers. So we talked about make a pair, seasonality, all that. Let's now switch our focus a little bit on the process equipment, because we said process equipment is the one that drives the make a pair anyways. So let's exhaust and make a pair. So let's worry about the processes a little bit. So two things: process equipment, ovens, furnaces, those kind of things, and energy converters, boilers, air compressors, those types of energy converters. So how do we define heating efficiency? It's a minimum heat to meet required quality requirements divided by the energy we invest into the process. That's the simplest way you can look at your heating efficiency. You can have it any number of ways. You can do all sorts of formulas. But essentially, how much heat you need to create your product divided by how much heat you actually pay for to put into that system. Simple as that. So if you look at it that way, in simplified form, it says heat to load, what actually goes into your load, into your product, divided by the gross input energy. That's your heating efficiency. So we'll use that terminology for the sake of this workshop. So if we reduce the energy we invest into the process, we will increase our heating efficiency, and you will notice that we're not touching the heat to load. Everybody is always very careful, very justifiable, to not affect their process. None of the things that we suggest will actually affect your process. Your process will remain the same. What will affect is the losses along the way. So you will put less energy into the system. You'll still get the same heat to your load. It will not affect the process. So how do we know that? Well, you have heat to load, and then you have all these other losses: stored energy, opening losses, material handling losses, shell losses, exhaust losses. You have to do the energy balance rather than the air balance now to find out how much actually all of that combined turns into your gross input energy. All of those arrows are some sort of losses except for the green one. That's the one that you need. So anything that's not heat to load is a loss. Opening losses, material handling losses, exhaust losses, shell losses, blowdown losses, for example, on the boilers. All of those losses represent a significant part of your energy. You paid for them, you didn't use them at all. You're paying for something you're throwing away. So if we minimize or cover our openings, we're going to reduce the losses. Many people have switched, especially on the finishing lines, they switch the size of what they do. I've seen many people who have, say, 3-foot wide openings by 8-foot tall openings into the oven, and they have parts like this size going in, because way back when the oven was designed, it was for bigger parts. Now they operate with the smaller parts. Well, close off those if you can. Maintain or increase the insulation, another part. And people usually take that to add insulation. I would not advise that blindly, because what will happen, insulation is designed to be a certain size, and if you just put additional insulation on the insulation you have, you could create potential for condensation there. You could actually degrade your equipment much faster than otherwise. So what I mean by maintain or increase the insulation, if you have, say, 4 or 6-inch panels, can you afford and put 8-inch panels? Does that make sense? But more importantly, do you have any gaps? Did the insulation get squished around the metal structure? That's where you're going to get a lot of heat losses. Fix that first. Maximize the loading of the conveyors. Many, many finishing lines will have conveyors that carry the parts. Those conveyors, believe it or not, will take more energy than your part itself. So if you have 1 hook loaded for every 20 hooks unloaded, that's where lots of your energy goes. You're just heating that chain that goes around your facility. Yes, it heats your facility, but not in the most efficient way. Reduce the operating temperature. This happens a lot. Over time, we all are nowadays working under lean conditions. There isn't that many of us in the facilities anymore. Maintenance is stretched to the maximum. Over time, these ovens don't operate as they used to. They get plugged up. For the operator who actually is responsible for turning the widgets out, The best way to deal with that is just to turn up the temperature a little bit. So the set point of 375 at one point is now 450, and nobody cares because the widgets are going out. Well, that 450 to 375 generates a lot of heat losses. So take a look. Maybe it's worthwhile cleaning that oven every now and then. Minimize the exhaust volume. This is a big one on finishing lines because exhaust represents a significant part of your losses. And it's a total waste. And we'll get to that in a little bit more detail. So for example, Class A natural gas fire convection oven, which is the most finishing ovens in our province, will have something called purge requirements, which means that you cannot start the oven. You cannot provide the flame to your burner until you exhausted 4 times the volume of the oven. So every time you start the oven, you have to exhaust 4 times the volume of the oven out. All of our ovens, or most of our ovens, are fairly old, 20 years, 25 years, 40 years, not uncommon. At that time, there was no VFDs. And none of you would be willing to wait on your process to purge the process every time you have to restart it for like 2 or 3 hours. So they put the fan for the exhaust was sized to minimize the purge requirement to about 10 to 20 minutes. You want it purged quickly. VFDs were not very common then, so you were running that exhaust all along. You don't need it, but you were running it because that was the only way to do it. But really, operational requirements, and we had workshops on that, we'll have it in the future as well, they're just representing a fraction of that purge volume. Very small amount. You really need to, in today's finishing ovens, most of the time, you just need to exhaust enough to get rid of the products of combustion. Solvent is only like 9% or something of your loading, very small. So to get from purge requirements to operational requirements, today we can do that with VFDs, relatively inexpensively, relatively cheaply. So that's what we recommend doing on most of the finishing ovens. We had great success with that. We have saved people a great amount of money. We went from 5,000 CFM of operational exhaust down to about 800, 900 CFM of operational exhaust. And that represents significant savings. For some of them, represented almost 100,000 cubic meters a year in savings. And again, process was not affected. There was nothing that changed on the actual part that went out or the quality of the paint. So with VFD, you have 2 modes. You can have a purge mode, so the motor goes all out, 1,800 RPM, pulls out all the exhaust as fast as possible. Once that's done, then it goes into regular production, slows down the fan, exhaust runs slower, and you can exhaust far less warm air out of the oven. How much savings is possible? This is a graph that I've gotten from one of the suppliers of these ovens a while ago when I was still buying these ovens. So they did it for us. This is typical in the industry. This is what we find as well when we do calculations for your particular facilities. If you have 100 units of energy going in, these are the opening and shell losses. You will see that shell losses are about 16%, significant but not huge. You will see that material handling loss is bigger than the shell losses, so it's more. And this is for well-operated oven that's properly loaded. So if you have 1 hook loaded every 20 hooks, that goes way up. And look at the exhaust loss, 44%. Half of the energy you put into your oven gets up and out of the exhaust. And what goes into your product is only 22% of your investment. Every $100 that you put into the oven results in $22 worth of value. Or to look at the other way, you only need to spend $22, but you're spending 100. And 44 of those dollars goes up the stack. So you can save, even if you reduce it only by half, you save 22%. 22% of your energy going into your oven can be saved by doing that. So we'll do another example there. Paul Morrison will do a quick show of, we built a little oven as well. Just like we built the facility, we have a little oven, and Paul will show how that works. And you can ask him all sorts of questions. He's been around ovens for a long time, slightly longer than I have, hopefully. Feel free to jump in and ask him questions. Thank you, Paul. That was good. Yeah. Okay. So let's continue on. We have quite a few slides to go through. So any more questions on this before we move on? One thing to keep in mind always when we do these exercises, these are typical things that we see. That doesn't mean that it applies to you directly. This is one of the reasons why we insist on energy solution consultant going and talk to you about your processes. That's why we don't just give you now a coupon and say, go reduce your VFD by 30%, here's the savings. We can't say that. There is no point in doing that. But what we can do is help you understand how your process works and quantify the benefits. So many people will say, well, I can't turn this down because of this, this, and that. But that's because they never put a dollar value to the turning it down. It's one thing to say, I'm going to turn it down because it's a good thing, versus I'm going to turn it down because it's going to save you $100,000 a year. Those are two different propositions to the management. And we'll give you that as well. So that payback is included in our proposal as well. And as Dan pointed out, right now we actually are expecting the results from one of the air balancing on the paint line system. So we do that and support it as well. So we know that this exhaust contributes to the losses. We also know that most of us today use significantly less solvent than they did before. So we know there's potential for savings almost in every single oven. I would be surprised if your oven is any different, but that's why we have to investigate it. The other thing that people are always worried about is that reduced exhaust will actually let them leave them open to leaking oven exhaust out into the facility. But you would be surprised how many of those places actually don't do that because of the reduction of the oven exhaust, but because of the negative pressure in your building. And I've had people say, no, my ovens are tuned for that condition. No, your ovens are tuned for that conditions because you had a condition. They were not meant to go into that condition in the first place. Every oven is designed for ever so slight negative pressure. But it doesn't mean that you have to now fight that negative pressure, the huge negative pressure around the oven. And this kind of process of losses just multiplies along the distribution system. You have the same losses in the delivery system as you had at end use. You had an energy converter, same type of loss. One of the energy converters is the boiler. Air compressor is even worse, but boilers are something that thermal energy is being used at, so we know something about the boilers. So you look at the boiler, typical steam boiler, out of 100 units of energy going into it, steam only takes 76.5% or 76.5 units. The rest is being lost. Shell losses, blowdown losses, and exhaust losses. Again, significant losses in the stack, 20%. Not as bad as the oven, but significant nonetheless. So what do you do with those? How can you improve your boiler efficiencies? Well, you minimize the blowdown, because that's one of the ways you lose your energy. You heat it up, you create steam, and then you just blow it down the drain. You maintain or increase the insulation. Some of the boilers have been old, and they have really torn insulation, replace the insulation. Exhaust volume. What are you going to do with the exhaust volume out of the boiler? 20%, significant. Well, unfortunately, on a boiler, it's not as simple as just turning down the VFD. That's not how it works. Every boiler, if properly maintained, will have a certain amount of volume that needs to be exhausted, and that's it. You're stuck with it. So we are really talking about recovering the heat out of that exhaust rather than reducing the exhaust itself. So now that we know that we have to live with the 20% losses in the stack, can we recover that heat somehow? And going back, thinking of our formula about heating efficiency, heat to load divided by the input energy, if you think of the Sankey diagram, and if you can recover some of that loss, put it back into the system, you will increase your heating efficiency, just like you did by reducing that loss in the first place. So step one, can you reduce the losses? If yes, reduce them. If you cannot reduce them, recover the waste heat that those losses generate. So flue gas heat recovery, economizers. Everybody knows about that on the boilers. That's one way to recover your heat, waste heat. Blowdown heat recovery, also a very popular thing. It comes on a skid. You attach your blowdown, you recover heat. Condensate return. A lot of people don't realize how much energy is still in the condensate. If you don't return it properly, how much energy you waste. Again, our energy solution consultants are available to discuss your particular situation, your particular setup. Feedwater Economizer. Most of you are familiar with the term Feedwater Economizer. Most of you know what it is. It's relatively inexpensive to implement. You put a coil essentially around the stack, put the boiler feed water through it, and you recover some of the heat out of it. Both heat source and sink are functionally connected, so it's simple to operate. If the boiler operates, feed water is being used, and the Feedwater Economizer is being used to recover the heat. Savings, typically around 3 to 5%. If anybody tells you that they're going to save you more than 5% with the Feedwater Economizer, call us before you spend the money, please. They are probably deluding themselves. So I would not trust. I've usually 3 to 5%. 5% is on the high side. 3% is more likely. So if anything goes out of those numbers for Feedwater Economizer, question it. The problem with Feedwater Economizer, you're leaving a lot of heat. So for example, if you have a Feedwater Economizer there, and you're getting the flue gas temperature 450 degrees F out of your boiler and into the economizer, it's going to leave at about 320 degrees F, which means that 300 degrees is still pretty warm exhaust. And Feedwater Economizer is designed in such a way that you cannot get flue gas temperature down below 300 degrees F by much, because then you're starting to be in the danger of condensing, and that's going to eat your Feedwater Economizer, which will not be good for your payback periods. So the only way to recover heat is to put the boiler feed water, because that's the only thing that's warm enough or not cold enough that can be put through the Feedwater Economizer. That's why you're leaving a lot of heat. Because this, if you were to put something cold through here, you would condense there, you would ruin your Feedwater Economizer, that would be the end of the story. So you're leaving a lot of heat still available going out of the stack. That's why you have condensing economizers. You will often see them as a heat exchanger installed either in stack or on the side as a separate installation. If it's more expensive because it's corrosion resistant, but it recovers latent heat as well as sensible heat. Again, we have different workshops where we discuss the benefits of latent versus sensible heat, but latent heat is just to say that we can actually condense some of the water out of the flue gas. By condensing the water, you're getting the energy that was needed to vaporize the water in the first place back. And that's actually where the savings are. So if you look at a condensing economizer, this is a typical boiler room, very simple one. You have the Feedwater Economizer already. You're using it to preheat the Feedwater Economizer. It goes back to your deaerator. You have condensate tank that mixes makeup water and condensate return. The more makeup water you have, the more energy you have to put into your DA, which means less efficient your system is. So now we can put condensing economizer on top of the Feedwater Economizer. So once the flue gas leaves the Feedwater Economizer, it goes into condensing economizer, and you can put cold makeup water, that's it, and put it back into the condensate tank at the end of it, preheating your makeup water. The benefit of condensing economizer, as we said, it can recover latent heat, which means it can condense, which means you can put cold water in it, and you'll get up to 60 degrees F of the flue gas temperature leaving the boiler. Now, if somebody is selling you condensing economizer and tells you that they're going to get 60 degrees F flue gas out, I would not want to do that. I would want to keep it at about 90 to 100 degrees F, even if I leave some energy wasted. And that's because I've seen installations where you go down to 60, 70 degrees F and you generate your own weather system on top of your building. Because when it comes out that cold, it immediately condenses and it creates like a little puddle around your stack. So I put there 60 degrees F because it is possible technically, but I would leave it at 90 degrees F, 100 degrees F, you're good to go there. But to me, the benefit of condensing economizer is not that. That is good application for those who only run boilers. But for most of us in the industry, we don't run just boilers. We also need water. We need process water, a lot of process water that we heat in something else. So I like condensing economizer because I can take my process water and put it through the condensing economizer. So it's not tied to my boiler, it's tied to my process. Whenever I need hot water, I put it through the condensing economizer. I can get it from 50 degree F city water to 170, 180 degrees F water on the other side, for essentially waste heat out of the stuff that I'm already paying for. So it's not a net new source of energy. That's the benefit to me of the condensing economizers. And when I had the best examples of implementations, that's how I implemented condensing economizer. As a matter of fact, I didn't even put Feedwater Economizer on the system. I just put the condensing economizer, and it didn't tie it to the boilers at all. I tied it all to the process. And we saved close to 700,000 cubic meters a year. You'll see that example later. So condensing economizer, it's more expensive to implement, yes, but can be used with multiple boilers. So you can feed 2 or 3 boilers into the same condensing economizer, which means that you don't have to pay 3 times for the same equipment. And it's not for makeup water only. It can be used for your process water requirements. And if you use a lot of warm process water, this is a great opportunity to save. Savings are typically 10% in the condensing economizer alone. Remember the Feedwater Economizer, 3 to 5%? This one is 10%. And the way that I implemented it in one case, I actually just had condensing economizer recovering 14% of the energy all in one. So instead of having 2 different pieces of equipment, I just had one that recovered all of it. So how do you know if condensing economizer, or any economizer for that matter, will help you out? How do you know if you waste energy in your stack? Well, you need to do boiler flue gas measurement. You need to develop boiler heat and mass balance, and then find somebody who will install that for you or give you a quote for it. And all of that can be helped by us. So we have often questions what the flue gas measurement looks like. We often have people calling us and say, hey, can you come and help us install the economizer? We ask, well, what's your boiler flue gas look like? They're like, oh, it's good. It's like 80% efficient. But when we ask, can you have a strip of tester? Most people don't know that strip even exists. So today we thought that for about 2 to 3 years simple payback, it's worth our while a little bit for Chris to talk about boiler flue gas analyzer. So if you don't mind leaving the tables one more time today, and Chris will show you what your combustion strip should look like, how you get there, all the good stuff about combustion. Chris? So thank you, Chris, for that. That was good. Again, a reminder for everybody, this piece here is the most important piece of paper you can get if you ever get somebody to do your combustion testing. Because we have people usually come do their combustion testing once a year, and they can never produce their test strips. The one thing that we have to keep in mind, key points, flue gas temperature on that one, get that, so you know how much heat you're putting out the stack, how much oxygen is in there, how much carbon monoxide, and combustion efficiency. Now, there's a big warning that I would put. Unless this instrument was calibrated properly, operated properly, weighted properly, I would not trust combustion efficiency at all. I would use the chart that we gave you. You take the temperatures, you take the oxygen levels, you will get much better results if you look at the chart than you would get from these strips for efficiency alone. Most of them are not that well calibrated, and most of them will be off. Depending how complicated their algorithm is to calculate efficiency, you will get sometimes close, sometimes widely different numbers, but never the same. So I wouldn't rely on that as a gospel to say this is what my efficiency is. I would look at the other factors. So when we do project for you, when we want to evaluate how much savings can we get out of the economizer, for example, these are invaluable for us because then we put the raw numbers for the temperatures, oxygen, all these gases, and we calculate exactly what your efficiency is, and then we can calculate exactly what the savings are going to be. We've done that for years. We're pretty good. We can do a quick calculation, give you plus minus 2% savings levels. Any questions or comments on this particular? No? Okay.
Even this is more useful the more gas you burn. Like if you have an appliance and or something uses a lot of gas.
Yes.
And the burner is susceptible to fouling or poor adjustment.
Correct.
And this is more worthwhile, right?
Correct. I had one customer actually did combustion testing on all of their HVAC units, even including the unit heaters. And we found that 25-year-old unit heater was operating at about 80.1% efficiency. So if somebody tells you, oh, I have old unit heaters, I'm going to put the new ones, and you're going to save 20% of your energy, call us before you spend the money. So what have we learned so far? What are the ways you can actually influence energy consumption in your facility? Exhaust, type and volume, makeup air volume, indoor temperature settings. Lots of people have the same setting whether they work or not. Even when the facility is empty on the weekends, they still leave everything operating, including the makeup air units, which is really odd. Process control strategies. Are you using proper set point controls? Are you going into idling when you can? Waste heat recovery, now you looked at everything, all the potential for reducing the waste is used up. Can you recover some of the waste heat? Paul has touched there an example of that oven. We had a customer who reduced the oven exhaust, and then they put a heat exchanger where they preheated the air going back into the oven, and that reduced the load on that recirculating fan. They saved about, I think it was 1 year payback on $30,000 investment. And of course, preventive maintenance. Making sure everything runs the way it was supposed to be running is a great way to save energy. So what does experience tell us? Those are all the ideas that we have, but really, we often find that analysis paralysis rules. Everything seems so complex, I'm not going to do anything, that's it. Well, but that's not the right way to do it. If you don't have money for implementation, if you don't want to upset employees, there's ways to get around it. We actually implemented one of those exhaust reduction in the facility systems where we saved 1 megawatt of electricity in a unionized facility by working with the union, indoor air quality technicians, and their maintenance, and we convinced them that actual quality of air improved once we reduced the exhaust. But it required that maintenance person who worked with me, the maintenance manager, to be really patient and explain the process to the union, get them in, and we got everybody agreed that this is the right way to do it. They saved something on the order of 400,000 cubic meters in gas, 1 megawatts in electricity by doing that project. So in today's environment, is this do-nothing option even feasible? There's all these things that increase the scrutiny on our facility. We need to use less carbon. We need to be cheaper. We need to be green. So given all of that, how do we get there? How do we actually move from thinking about the action into action? So what I like to always say is make energy visible. We talked about here before. We said, oh, savings would be great. But nobody says how much in savings. And that's because nobody knows how much energy they actually use. Very few facilities, even today, have a display in the facility, on the floor, how much energy did they use this hour. And that's a great motivational thing. If you don't see it, you will never have any impact on it. How much does it cost you to run it? So you have to make energy visible. Once you make it visible, then you have something to say, okay, we're spending $100,000 on this. So 10% savings will be $10,000. Is this worth our while? It's much easier to visualize the savings and to visualize the benefit if you know what it costs you in the first place. So going back to my 3 R's, reduce, recover, and replace, let's take a look at the first one, reduce. These are some examples of real-life projects. I'm not mentioning the names here on purpose because it requires more involvement, but these are all real projects. So if you recognize your project, great. If you want to talk about it, perfect. If not, that's good too. Reducing is an underutilized strategy. We have always done it this way. Why would we even do anything different? What's the point? And risk is great. I fully admit that. When you make a coil every 4.5 seconds like we did, and you screw something up, you will have a lot of energy to make up that loss in production. So we all understand that. We all come from the industry. We all understand we don't want to play around with your settings just for the sake of playing around. But that's not a reason to keep them the way they are just because we're not willing to do anything else. The best part of this reducing is that there are always, or almost always, no cost or very low cost opportunities. Changing the set point doesn't cost anything. And it's easily reversible. Even with VFD on the exhaust, as Paul mentioned, if you need to go back up, you turn it back up, you're back where you were. The risk is minimum. So why not explore that potential? For example, exhaust reduction project. It's one of the facilities that we did a couple of years ago. There's investment up there, including the audit, design, and installation. It was done by their internal people. $44,000 was spent. They avoided 790,000 cubic meters of worth of gas, which equals about $200,000. They avoided 1.2 million kilowatt hours in electricity by doing that. And we gave them $17,000 incentive for their, in addition to their savings of $346,000 a year. Every year they will save $346,000 for $44,000 investment. This is the same facility that called us originally and said how much incentive can they get if they use direct fired makeup air versus the indirect fired makeup air. Because they were, Slobodka, how much were they under? 250,000 CFM? 250,000 CFM of exhaust that they wanted to make up by putting 250,000 CFM of makeup air into their facility. 800,000 cubic meters saved. Their current bill, and the bill before that was about 400,000 cubic meters. So they would triple their bill. Not even talking about electricity, just natural gas bill. They would triple it if they went with their original idea. And yeah, they would do it very efficiently. They would do it with direct fire and makeup air, so it would be more efficient than indirect fire. Congratulations. You saved yourself $200 on a $200,000 investment. Right? And they were, first 3 meetings that we had, they were absolutely adamant they need that exhaust air. They needed it, and they would not budge. In the end, the guy who was maintenance manager, who was the staunchest supporter of exhaust, we need him, was actually executing this project himself and done a fantastic job. Now he's got on his little PLCs around the facility. Not only does he have all these interlocks and how it works, he also has how much he saves every hour. So when you go there, you can press the button, and it tells you how much electricity and natural gas you saved. He did it himself. No third-party vendors, no nothing. So payback, 0.12 years. I don't even know what that is, a month. They also saved 1,490 tons of carbon dioxide equivalent. So pretty nice. Recovering. So that was a reduction example, but recovering. One of the things that heat recovery I found when I went into energy field first, I found it to be way more complicated than it needs to be. Everybody wanted to sell you this off-the-shelf solution that was very engineered. It had all sorts of heat exchangers, all sorts of inputs and outputs, but it cost like $1 million. You'll never pay that back. That's just not going to work. So when we talk about recovering, let's talk about simple recovery. Let's not talk about packaged solutions. So the good ones, the good projects are always low cost and simple implementation, and payback of around a year to 2 is about average what we get out of these types of projects. So what is it an example of? So let's say you have makeup air unit. You put money into the powering that makeup air unit, some natural gas, some electricity. You take the outdoor air that's cold, you heat it up, you dump it into the facility. At the same time, you have a whole bunch of electricity users in your facility. And when I talk electricity users, that can be anything. That can be your motors, that can be your VFDs, that can be your air compressors. Air compressor, 80% inefficient unit. Like, I can't believe that that's still, everybody talks how inefficient boilers are, but look at air compressors. So you have a whole bunch of electricity users. Any one of you ever stood next to the bank of where the VFD drives are, panel? You notice how warm it gets? That's because when you do VFD and you throttle it down, guess where the energy is going? In the friction here, it gets tossed into heat and gets tossed out. So VFD is not inexpensive. It's not cheap. And it's not free. So to use some of that heat, let's say we can take some of that heat, put it through some sort of heat exchanger, preheat the air before it goes into makeup air unit, and you reduce the amount of money you're going to spend on your makeup air heating because the delta T will be smaller. But that can be a fairly complex thing to do. It's possible. For some, it's very doable. It's still within 2-year project for most, but we can do better. What if we just took that heat, put some air socks or the fan, and distribute the heat around the place? And you're talking air compressor heat. It's not like it's polluted or anything. It's just regular heat. Most people have giant big ducts that take that heat and dump it out the door on the other side of the wall, right outside, heating up the area and community. And then they will put a whole bunch of money in the makeup air unit to keep it warm. So why not just do that and reduce the amount of air that makeup air unit needs to make up the temperature ones, and then you'll save the energy. And you have to remember, electricity is not free. This heat that every electricity user uses is not free. You paid for that electricity. It just happens to turn into heat. So let's look at the air-cooled air compressor project. We talked about it before. 80% of all the energy, so if you're 100 horsepower compressor that you're so proud of, 80 horsepower of that is heat. You get no use of it. It just needs that heat to turn regular air into compressed air. So these guys spent $7,000 for about 1 year, half a year payback after our incentives to reduce their natural gas usage by 30,000 cubic meters. They simply, for $7,000, they put a duct, they put a damper that said, in the summertime, put that heat outside. In the wintertime, put it inside. They had a little fan. That was it. They recovered 30,000 cubic meters of air, of natural gas, and they saved $8,300 every year. Simple project. No impact on production, no impact on anything. They did that like on a regular workday. They also saved 55 tons of CO2e. Not a big number, but then again, the investment was small. It's a very simple, no-brain thing to do. This one is a little more complex. It's a water-cooled air compressor project. We came through that project because we were walking by the compressor, 300 horsepower compressor, that was right next to the boiler room, that was right next to the 2 pipes that went right above the compressor. One pipe was going compressed cooling water into the cooling tower. The other one was bringing the city water and going into the boiler room. And we said, well, why don't we just put a heat exchanger between these two pipes? It reduces your cooling tower load, increases the feed water temperature makeup water temperature going in. Everybody's happy. So they've done that. They had a heat exchanger on the books. They installed it themselves for $21,000, heat exchanger and installation. They saved 230,000 cubic meters a year. 230,000 cubic meters. That equates to about $65,000 in savings. That doesn't count for any savings that potentially is on the reduced cooling tower load, but it does account for all the savings in the natural gas. So instead of using 230,000 cubic meters of natural gas to preheat the makeup water for the boiler, they just use the waste heat that they already paid for anyways. We gave them $10,000 in incentive, 50% of the project cost, and the payback was 0.4 years. It's sometimes as simple as that. 430 tons of CO2e was saved. Same thing, exhaust redistribution project. We talked about it as an example before. We talked about how too much exhaust is bad. So these guys took too much of their exhaust. They were very much like this facility. They had a makeup air. They had, in this area, they had the plastics processing equipment that was generating a lot of heat. And to counter that, they had a bunch of, I think it was 80,000 CFM worth of exhaust up on top to get rid of that heat. Well, for $38,000, they shut off these exhausts in the wintertime. They put socks underneath here. They took that same 80,000 CFM fans and pushed the air here where the shipping area is. They saved 201,000 cubic meters of natural gas for $57,000, $60,000 worth of savings, and we gave them $20,000 worth of incentive. Nothing else was required. It's a switch that turns these fans off in the wintertime, turns on the fans in the air socks, and 3 air socks that go around their roof. Since then, they actually installed 2 more air socks to recover even more heat. They've never been as warm in the wintertime as they were last winter. And the funny story about this one was their management changed last year. They got a new plant manager, a new maintenance manager. These guys didn't know about the procedures of switching off the winter to summer mode. In the middle of the summer, people were starting to complain that they're very hot in the shipping door area. And they couldn't understand why, so they called us up and we're like, which mode are you on? And I was like, what's the mode? So we told them, and they're like, okay, never mind. But they're getting 22 degrees Celsius in the shipping area in the coldest day of the winter, 22 degrees. All of their unit heaters are now locked out. They're physically locked out. People cannot actually use heat paid for. So for $38,000, not a bad payback, half a year. 379 tons of CO2 saved. Another one. This is a little more complex. So costs a little bit more, the payback, but payback is still within 2 years. These guys, for $102,000, what they had is, they had the same thing. They had the blow molding equipment on one side, then they had a big wall and a big warehouse distribution area on the other side of the wall. So here they had a whole bunch of heat. They had about, I believe it was 65 to 75,000 CFM of exhaust that was pushing that heat out. And in the warehouse, they had a whole bunch of unit heaters all around, and they couldn't keep warehouse warm. So finally, they got hip to the game, and they said, okay, never mind. They drilled a whole bunch of holes in their wall between the two areas. And instead of exhausting that in the wintertime, they actually put a bunch of radial fans in those holes that took the air from the warm space and dumped it into the warehouse. Again, they didn't need any of the unit heaters anymore in the warehouse at all. They saved 154,000 cubic meters of natural gas. We gave them $15,000 in incentive for that, and they saved about 300 tons worth of CO2e in the process. For this particular facility, that number here, even though it's not as big as one might expect, was actually more important than the savings up there because of their image. Another way to recover heat, if you have boiler and the water heater of some sort. One of my favorite examples, because this water heater, for example, was a direct fired water heater, direct contact water heater. Everybody will tell you 99% efficient, all sorts of stuff. But in their particular case, it was going into the loop. So direct contact water heater wasn't actually giving them any benefit. They were running at about 55% efficient when they actually looked at it. So what we've done, instead of taking all this money, putting it up the stack, and the money that goes up the stack from the other piece of equipment, we actually took some of this exhaust, preheated the air going into direct water, and reduced the amount of energy needed in direct contact water heater. In the end, we actually ended up eliminating direct contact water heater altogether and using only the boiler for all of it with the condensing economizer. This is why I love condensing economizers. If you're going to do anything and you have process water requirement, condensing economizer is the way to go. They invested $276,000, which is not a small amount of money, but they saved 700,000 cubic meters of natural gas. They saved, they added a little bit of electricity load because you need a fan for the condensing economizer because it was one of those off-the-stack installations. But they still saved $162,000. We gave them $67,000 in incentives for about 1 year payback. That facility now actually runs the most energy efficient facility in their global network because of the project like that. This reduced their KPI, energy per widget made, by about 40%. So they saved 1.2 tons of CO2e, or 1,200 tons, sorry. Oven exhaust project, I talked about it earlier. For $30,000, what they've done is they took exhaust, remaining exhaust out of the flue gas out of the exhaust of the oven. They put it through the heat exchanger to preheat the air that went directly back into the oven. So they use the savings year round. Rather than putting it to HVAC, they use it back into the process. They saved 100,000 cubic meters of natural gas by doing that for $30,000 investment. We gave them $15,000, 50% of the project cost back, and their simple payback was just over half a year. And it still runs very nicely. So the last one is replace. So now that we've done all the other things, we recovered what we could, we reduced what we could. Now, sometimes we really have, the best option is to replace the piece of equipment. Sometimes you just can't do anything else. So if the equipment has failed, we have to replace it. If we have found some new functionality, if we have, remember that graph where we have some advantages in the marketplace and that's our benefit, maybe we've invented better mousetrap and that better mousetrap needs a new machine. All sorts of things can happen that we really need new piece of equipment. But every time we do that, the goal should be to gain quantifiable energy efficiency as part of that installation. So for example, if you're investing $1 million into a new oven, and it costs another $100,000 to make it really energy efficient, more than the typical oven on the marketplace, we will give you 50% of the cost. We'll cover 50% of that. So your delta is much smaller now. You would already spend $1 million, but you didn't have to spend that $100,000 on the more efficient equipment. Now you're going to spend $50,000, and we'll tell you how much you're going to save as a result of it. We'll confirm vendor savings. That's a great time to actually do energy efficiency, because last thing you want is pay for the new piece of shiny equipment, install it, spend $1 million, and then go next 3 months to the management and say, hey, I got a better idea how this will work better. It's a little late at that point. You want to do that as you're talking about new pieces of equipment. It's a least risk strategy because, as everybody here knows, that if you replace the unit with identical one, nobody will ever blame you for anything. That's the way it was, that's the way it's now, I didn't do anything. period. But the problem is that you don't realize all the potential savings. And the rub is that you may not actually solve the problem that old piece of equipment had. And then what that does is doesn't resolve underlying issues. Lots of people want to replace one heater with another, thinking that that's going to now make it more efficient. It's going to give them more heat. It doesn't. And now everybody's still mad at you, and you spend the money, and you can't go back and say, now I got even better idea, because nobody will trust you. So what we want to do is get away from that. We want to analyze the situation within the time period that we have. We all agree that if something fails, you have to replace it fairly quickly. We don't have time to do like months' work of investigation then. But we want to still take advantage of opportunity and say, is there something better? What is it? What is it going to cost me? How long is it going to take to get here? Cost of ownership might actually increase. That example of 800,000 cubic meters of natural gas saved, avoided, is because if they have done their way, they put makeup air units, they would actually be paying 3 times natural gas bill as they do today. So yeah, they would solve one of their problems, but at 3 times the cost. And of course, if you're energy efficiency manager and you say something that something's going to be accomplished with this piece of equipment, and it doesn't, credibility of all energy efficiency efforts goes down. You're all aware of the fact that if you overpromise something by 5% and you deliver 10%, you think everybody thinks you're a god. But if you overpromise something by 5% and you deliver 1% under, you're nobody. So this is the same thing. We have to keep that credibility going. So to ensure success, every time you replace something, understand where the energy savings are going to come from. Don't be just satisfied by the vendor saying it's going to happen. I hear a lot of times, for every 1 foot of the height of your wall, you're going to save 3% of energy if you do this and that. Well, okay, can I see how that works using one of these formulas, actual physics? What makes you think that? So you have to ensure you have a method of verifying the savings, and you have to have scope of work that incorporates the key elements to confirm. How are you going to know that the savings have been accomplished? Every one of you have bought a new piece of equipment. Any one of you have said, I want this piece of equipment. I want this robot to work at exactly 4.5 second cycle time. Otherwise, I'm not giving you the money. We put all of that in our scope of work. Yet we buy makeup air units. We buy all sorts of VFDs. We buy everything. Yeah, it is going to save. How much? 30%. OK, 30%. But nobody actually knows. Even worse, nobody even checks. So if you follow the business case practices every time you replace the equipment, which all of you do, plan, do, check, act, do the same for the energy side of it. Plan how much you're going to save, implement the changes, check it, and then act on that. Hold the vendors responsible for it. Because that forces you to objectively define the benefits. That will give you credibility in front of your management next time around. I told you I'm going to save 100,000 kilowatt hours. I saved it. Let's go do another thing with the savings. It highlights the cost of ownership. If you do all of these properly, just like any other piece of equipment when you buy, how much is going to cost me, what I'm going to get, how much is going to cost me to operate every single day. Same thing with this. And it builds a culture of energy visibility. If every time you buy a piece of equipment says it's going to use this much energy, that builds that awareness that energy is part of what we do. It's not given to us. Energy is not a fixed cost. It's what we use. So in summary, what we really want, this program that we have, all of us here are really passionate for you to get the savings. Because that's what we're after. We can talk all we want, but we want you to get the savings. And savings have to be based on some actions. If you don't do anything, nothing will be saved. It's not going to happen. But we want those actions to be based on the decisions. And ultimately, those decisions have to be based on knowledge. It cannot be based on my gut feeling. So one way, a lot of people think of reducing energy management and reducing energy by just reducing the cost of energy. So I'm just going to buy cheaper commodity. That's reduction. I'm done my job. But that's only one part of the cost-saving strategy. And I would actually argue that it's a smaller part. The bigger part is actually consuming less of that commodity. And when you ultimately think about GHGs and all that stuff, which do you have more control over? How much can you actually control the commodity cost, and how much can you control the usage of the commodity that you do? We said turning down your exhaust on the oven by half saves you 22%. How much do you have to bargain with your commodity supplier to get 22% of commodity cost reduction? I work for Enbridge, and I still see myself as a manufacturing guy, so I'm not here to pander to Enbridge. But I can tell you, you're not going to get 22% from us. Right? And I doubt that you're going to get it from LDCs, unless it's a plus 22%, but that's a different story. So you have the control of the consumption. You don't have control of the cost. So focus on consumption more. So if you look at all the benefits of these projects that I highlighted as examples, real-life projects, on average, cost $74,000 for $86,000 savings. And those savings have been discounted. I discounted the savings by 15%, just in case something happened, or maintenance, or this or that. So it's at 15% will discount the savings of average. So you're still talking 113% IRR. There is nothing in manufacturing that gives you that IRR today. You can manipulate your stock prices, but there is nothing you can do with your production to actually get that IRR. To help with that, on average, we gave $21,000 in incentives, and 580 tons of CO2 was saved. So those are all very good numbers. It's all worthwhile investing some time to work with us to actually get you the savings.